Every antenna we have studied so far is a single element. A single dipole radiates in a fixed donut-shaped pattern. You cannot change where the energy goes without physically rotating the wire. An antenna array solves this by placing several identical elements in a row and feeding them with controlled phase shifts. The spacing and phasing between elements create a new degree of freedom that lets the combined beam point in any desired direction without moving any part of the hardware. Start with the simplest array: two identical sources separated by a distance d along the z-axis. Both radiate the same element pattern, but the signal from each one travels a slightly different path to reach a far-field observer. The path difference depends on the angle theta and the spacing d. If we also add a deliberate phase shift beta between the two feeds, the total field at the observer is the sum of two phases, one from each element, offset by both the geometric path difference and the intentional feed phase. When we write out that two-phaser sum, a remarkable factorization appears. The total field splits into the element pattern, which is the radiation of one element alone, times a new multiplier, called the array factor. For two elements, the array factor is simply 2 cosine of half the total phase difference. The total phase difference, psi, equals kd cosine theta plus beta, where kd cosine theta is the geometric part and beta is the feed offset. This factorization is the pattern multiplication principle. Total pattern equals element pattern times array factor. Pattern multiplication means you can design the element and the array independently. The element pattern sets the envelope, the broad shape that each antenna would produce alone. The array factor then carves narrower lobes inside that envelope. If the element has a broadside null, no array factor can create a beam there. If the array factor has a null, the total pattern also has a null, even if the element pattern is strong in that direction. The final pattern is the product of both, taken at every angle. The power of this factorization is beam steering. When beta equals 0, both elements radiate in phase and the array factor peaks at broadside. As you increase beta, the peak of the array factor swings away from broadside. The beam tilts towards endfire without moving any hardware. This is exactly how phased array radars and modern 5G base stations work. Electronic phase shifters replace mechanical rotation, letting the beam scan across angles in microseconds. Two classic configurations deserve their own names. The broadside array uses beta equals 0, so the maximum radiation is perpendicular to the array axis. This is the natural choice when you want to illuminate a wide area in front of the antenna. The endfire array uses beta equals minus kd, which shifts the maximum along the array axis straight ahead. Endfire is useful when you need a narrow beam in one forward direction. Every other steering angle is simply a value of beta between these two extremes. Antenna arrays introduce three key ideas. First, multiple elements create an array factor that multiplies the element pattern. Second, the array factor depends on the spacing d and the phase shift beta between feeds. Third, changing beta steers the beam electronically, from broadside through any intermediate angle to endfire. This is the foundation of every modern phased array system. We derive the array factor for two elements, but real systems use tens or hundreds. Extending the same logic to n elements will reveal how the beam narrows as the array grows and how side lobes appear. That n-element generalization is the next step.